guess you're down here. Current topic is total internal reflection. That's where we left off at the end of the last recording. And a little demonstration. I've got a bent piece of plastic here. You don't need any kind of special high-tech materials or anything like that. I've done a similar demonstration with just a glass rod, like a chemistry lab makes stirring rods out of. Sooner or later, I will figure out where I want to. There we go. So we've got a neon laser. Backwards. Neon laser shining into the end of this plastic rod, and it goes and has all these twists and curly cues. And the thing to notice is that the light goes around all those curves, and you can kind of see it reflecting off my finger where it comes out the end here. It acts as a pipe for light. And in fact, if I can manage to get the camera into the right position, you can even, the plastic is a little bit milky, so you can see the beam going through it, and see it skips off the inside surface of the plastic there, kind of crosses over. You can see it bouncing off the opposite side there, and so on. As it goes around the sharper part of the bend here, it hits the surface a little more often. And yeah, that's a pretty good view there. You can see the beam bouncing off of the edges of the plastic, and then eventually, of course, it comes out there. So that's optical fibers using total internal reflection. While I'm doing demonstrations, here's another good one. It's about something I'll be talking about in just a few minutes. So we have, I'll put the camera about there maybe. We got this thing that looks like a little plastic flying saucer with a little toy piggy sitting on top of this shiny thing on top. And thing is, when you go to grab it, your fingers go right through because it isn't there at all. Once in a while, I manage to get a really gratifying response out of somebody, like maybe once every 5 or 10 years, somebody will kind of like shriek or squeal or something when their fingers go through it, if I manage to sneak up on them the right way. Anyway, where the little plastic piggy really is down in the bottom there. You see, this is up here. This is a reflection. What you have here is you've got a concave mirror that's, dark on the outside. This is the inside of it. The shiny bowl is a concave mirror, and the little plastic piggy is in front of it, right about there. And the mirror projects an image of it the way I'll be describing in a few minutes. The bottom is a second mirror. All that does is, see, if you have a single mirror, everything's backwards. I keep moving it the wrong way. If you have a single mirror with an object in front of it about maybe here, it'll form an image of it maybe about here. With the second mirror here, it just bounces the light rays back so that they converge in this area instead of somewhere over in here. But well, for one thing, kind of illustrates you don't have to have a screen for the image to exist. The image exists with or without a screen. It's just you go someplace like a movie theater, and it makes it easier for everybody to watch the movie when you project it on a screen instead of having them all stare into the projector. But magicians love this kind of thing, smoke and mirrors. It's very easy to make something disappear if it wasn't really there in the first place. So we'll pause there again. Last thing was total internal reflection. And I think I pretty much took care of that at this point. So, and you know, there are other things I could say about reflection and especially refraction. There's only so many minutes in a course and you can't say everything. I could get into mirages and rainbows and, you know, there are a number of things that are interesting things, I think, that are a result of refraction. But the main topic of Unit 11 is lenses and mirrors. So we'll get into that. Lenses, of course, work by reflection. Lenses work by refraction. You can either bounce the light rays where you want them to go, or you can bend them where you want them to go, which is what a lens would do. So we're going to, as far as mirrors go, we're going to, for the most part, concentrate on concave mirrors, which would be when you've got a shiny bowl, as opposed to having the light rays hit the other side where you'd have like a shiny dome-shaped thing. That would be a convex mirror. Or a flat mirror like you probably got hanging in your bathroom where you comb your hair in the morning. Let's start out by considering well, first of all, we're going to talk about a spherical mirror in particular, which is not actually, for some purposes, the best possible shape. You get the clearest image out of a parabolic mirror rather than a spherical one. But if the mirror is a fairly small part of a sphere, there's not a lot of difference. And spherical mirrors and spherical lenses are pretty common because they're easy to make. So the idea is that this mirror you're looking at on the bottom of the page here is a part of a big shiny ball. Like maybe you had one of those glass Christmas tree ornaments that's nice and shiny, you know, and maybe you've also got a cat, which when you put them together quite often adds up to a broken shiny Christmas tree ornament. So when you had the whole glass ball, point C would have been the center of it. And we call it the center of curvature of the mirror. And what we have here is like a little fragment of, you know, if you had the whole thing, it would go all the way around, sort of like that. Let's say you take your concave spherical mirror and you allow parallel light rays to fall onto it. The easiest place to get parallel light rays is to use sunlight, okay? There are other ways of getting parallel rays also, but you know, the sun is almost 100 million miles away. And at that distance, any rays that are not parallel to each other are going to miss the earth. They've gone off in some other direction. And so, I mean, yeah, if you want to talk math class, perfect. They're not perfectly parallel rays, but that only matters if you're doing like 20 significant figures or something like that. Anyway, this light ray here comes along and it bounces off the mirror. And as it does so, it obeys the law of reflection. I may not have drawn it perfectly here, but hopefully the way it should have come out was that the angle of incidence here equals the angle of reflection there. And so that bounces the light ray downward. This ray that comes along on the bottom also obeys the law of reflection as it bounces off. See, a normal to the surface would be a radius of the sphere. So I've got all these little dotted lines drawn to the center of curvature. And it's one of those theorems from geometry class that a radius hits a circle, or in this case, a sphere, perpendicular to the surface. perpendicular to a tangent, I guess is probably the way they would put it in a math class. Anyway, a radius is a normal to the surface of the mirror. Angle of incidence equals angle of reflection. So the ray on the bottom gets bounced upward. And if you drew a whole bunch of other rays, you would find that they all cross, after being reflected, they all cross at the same point called the mirror's focal point. And this is actually where the imperfection of a sphere, this is just a little footnote. It's something you don't have to know. But with a spherical mirror, actually the rays that hit the outer part of the mirror cross at a slightly different distance. I believe it would be closer. I'd want to look it up before I said for sure, but I think it's a little closer to the mirror than the rays bouncing off the center part of the mirror. It's a defect called spherical aberration. So the light rays don't all hit exactly the same point from a spherical mirror. They just pass pretty near each other on the way out. To get a perfect focal point, that's why you want a parabolic mirror rather than a spherical one, a paraboloid to be precise. But don't worry too much about that. Like I said, we're going to assume this is quite a small piece of a sphere, so it's not much of a difference. The distance from the mirror to the focal point is called the mirror's focal length, which I labeled there with a lowercase letter f. And if you do a little bit of analysis of the situation, which we'll save a couple of minutes and skip over that. If anybody really wants me to prove it to you, I can, just ask. But it kind of looks in the picture as if the focal length looks like it's about half of the radius of curvature. And that turns out to be exactly true, as it says at the very bottom of the page. If you want a mirror with a 10 centimeter focal length, you want to make it with a 20 centimeter radius of curvature. So let's see, every point on the mirror is the same distance r from point C. That's what makes it the radius of the sphere. F is the focal point, the point where parallel light rays converge. Right, okay, so I've said all that, I can turn the page. On the top of the next page, as I said a minute or two ago, pretty much anything you can do by bouncing the light rays where you want them to go, you can also achieve by bending them where you want them to go instead. And so instead of a converging mirror, we have here a picture of a converging lens. And that's a minor variation on the same story. Once again, parallel light rays hit it, such as sunlight. And after passing through the lens, the rays that hit the upper part get bent downward. The rays that hit the lower part get bent upward. If you want to follow it in a little more, this is supposed to be seen from the side. Okay, if anybody doesn't quite get what the picture is a picture of, you've got your basic magnifying glass like this, and you're looking at it from the side here. Okay. So if you think back to the Snell's law problem that was a page or two back, that showed that when light goes from air into glass, it gets bent toward the normal. You've got a smaller angle in the glass than you do in the air. And when it goes from glass back into air, again, it follows from Snell's law that you have a smaller angle in the glass and a bigger angle in the air. So if it's just passing through window glass, where the two sides are parallel to each other, comes out the other side of the window and gets bent back to its original direction. But this is not window glass. The sides are not parallel to each other. And so as you can see with the glass shaped like this, the upper rays get bent downwards, the lower rays get bent upward. And once again, you have a focal point where what were originally parallel rays cross. One difference between lenses and mirrors is that a mirror has just one focal point, because if you flip it over and let the light fall on the other side, you've got to convex mirror now instead of a concave mirror. With a lens, if you flip it over and let the light fall on the other side, it's exactly the same situation. So if you've got light rays coming from this side and they pass through the lens, they'll converge on a focal point over here to the left of the lens. So a lens has a focal point on each side, whereas a mirror has only one. Well, what if the light rays aren't parallel to each other? Instead of the sun or the moon or a star or something, what if your light source is just a few inches away, like this candle? Well, let's follow some light rays coming from the tip of the flame on that candle. Ray number one, this is a mirror. You could draw similar diagrams for a lens. As we go on through this, by the way, a lot of the emphasis is going to be on how to draw ray diagrams. That's just simply because, it's not because ray diagrams are more important, it's just simply because it seems to be what people have difficulty with. When we get to the equations you use to solve optics problems, well, that's just throwing numbers at this week's equation, and you've been throwing numbers at equations for quite a while, since the beginning of the course. The ray diagrams are something that seem to take a little more getting used to, so I spend a little more time on them. Anyway, ray number one approaches the mirror parallel to its axis. The axis, well, the formal way to define it is that it's the line that passes through the focal point in the center of curvature. But, the basic idea is it's this line that sticks out of the middle of the mirror, kind of perpendicular to the mirror at that point. Anyway, a ray that approaches parallel to its axis passes through the focal point on the way out, because that's what we defined the focal point to mean in the first place. In the picture we were looking at a minute ago, all the rays were parallel to the axis, so they all went through the focal point. Well, here other rays are going off in other directions, but we still have one ray that's parallel to the axis, so it still goes through the focal point on the way out. Ray number two is the same idea, just turned the other way around. Angle of incidence equals angle of reflection, so if you switch which one is which, they're still equal to each other and things behave the same way. A ray that approaches through the focal point is parallel to the axis after being reflected. The third ray that can be drawn with just a ruler, as opposed to, you start drawing random rays, you have to get out a protractor and measure the angles, and with a lens it would be even worse. You'd have to measure an angle, use Snell's law to calculate the other angle, and then measure the protractor again. But if you stick to these three rays, you don't need to measure any angles. You can solve a problem using a ruler only. And the third ray that's on that list, number three, the way I've labeled them there, is the ray that approaches the mirror through the center of curvature. That means it approaches the mirror along a normal. And so it's gonna, if the angle of incidence is 0 degrees, the angle of reflection will be 0 degrees, and it'll just go right back the way it came. It's like having a ball in your hand and throwing it right straight down, perpendicular to the floor. It's going to bounce right back toward your hand if that's the angle it hits the floor. And that's what's going on with ray number three there. So to help you remember some of this, I put some ray diagrams, not a diagram for every conceivable case, but some ray diagrams are on your formula sheet to kind of give you some reminders. But summarize again, in parallel to the axis, out through the focal point, in through the focal point, out parallel to the axis, and the ray through the center of curvature goes back the way it came. In this diagram here, we have an example of what's called a real image. One way of explaining it as a real image is one that can be projected on a screen. If you imagine having this candle in a darkened room, and actually when we get to the lab for this, you'll be doing something similar, except you'll be doing it with a lens rather than a mirror. But if you imagine having this candle in a darkened room, so there isn't a lot of background light to wash things out, and if you held a blank sheet of paper, like a 3x5 card or something like that, something to use for a screen, you held it right here where all these light rays cross. Well, let's say the light coming from the tip of the flame is sort of an orangish color. All the light that converges on the screen at that point right there will be an orangish color. You could draw some more light rays coming from down at the base of the flame, and they would cross again just a little further up over here where it says image. And so if it was sort of a bright yellowish white down there, you'd have sort of a bright yellowish white there. You could even draw a bunch of light rays from way up here where there's nothing. And those rays would cross again here. And so on the screen at that point, you would have nothing. So there's a one-to-one correspondence between points on the candle and points on your 3x5 card over here. And because the light hitting each point on the card came from its own separate point on the candle, you'll get a little upside down picture of the candle flickering away on the screen at that point, okay? Or an image of it, a real image. A real image, the rays do pass through. That's the more fundamental way of explaining what a real image, I think, is. A real image is one that light rays do actually pass through. The fact that it can be projected on a screen is a result of that. A virtual image, on the other hand, that's what you have, for example, when you're, well, I'm assuming that somebody listening to me is not like shaving their head or something like that, but assuming you comb your hair in the morning or look in the mirror while you brush your teeth or something like that, that flat mirror in the bathroom produces what's called a virtual image, okay? And there'll be example, well, there's an example coming up just below here, only it's with a curved mirror instead of a flat one, but it's basically the same thing. A flat mirror and a convex mirror can only produce virtual images. If you want a real image, it's got to be a concave mirror. And even then, you might get a virtual image depending on where you place the object. So here where we got the real image, the object was placed outside the focal point. That creates a real image. In the second diagram down here, I guess I better boost that up if it's supposed to be visible. Now, the object, the candle in this case, is inside the focal point. Same thing. Let's draw some ray. Now, there's 3 rays on the list of rays you can draw. Actually, any 2 out of 3 will solve the problem for you. You can draw the third one as a double check if you want. But to locate the image and see how big it is, you're looking for the point where the rays cross, and you can see that from 2 of them. The only reason to draw the third one would be for like a little bit of extra fun. But they have to come from the same point on the object. And the idea is if they come from the same point on the object, they'll cross at the corresponding point on the image. So again, from the tip of the candle, ray number 1, just like further up the page, in parallel to the axis, out through the focal point. Ray number 2 is the same thing in reverse. Well, I can't say through the focal point when the ray originates closer than the focal point. So maybe I better rephrase that a little bit and say in along a line that passes through the focal point, okay? From the focal point to the tip of the candle, there isn't any light actually traveling along that line. But once you get to the candle, that's the line that the light travels along, a line that passes through the focal point. And just like in the other picture, that ray is parallel to the axis after being reflected. The third ray, the one through the center of curvature, well, there again, I can't say it approaches the mirror through the center of curvature when it begins closer than where that point is. So rephrase it and say it approaches the mirror along a line which passes through the center of curvature. There isn't actually any light approaching the mirror until you get to the candle. But from that point on, the light is moving along a line that goes through the center. And that's the one that gets bounced back the way it came. So if you're trying to solve a problem with a ray diagram, you draw these diagrams to scale, carefully measure everything, and you can measure your answers off the diagram is the idea. So you draw the rays I've just been describing, and then you look for where the rays cross. Okay, the one that's further up the page up here, that's where the image was, is where the rays cross. Well, in this one that we're looking at now, after you've drawn the rays, you look for where they cross. They don't really cross. As they move away from the mirror, they're getting farther and farther away from each other. Since they don't really cross, you don't get a real image. But here's your eye over here looking in the mirror. The rays enter your eye as if they came from here. Okay, this ray looks like it came from there. This ray looks like it came from there. All your brain knows is what the light rays are doing as they enter your eye. It doesn't have any way to trace the rays all the way back to their source. It just knows what they're doing as the rays come into your eye. And what these rays are doing as they enter your eye is absolutely identical to what would happen if there was a great big candle back here behind the mirror somewhere. And so that's how you interpret it, okay? A curved mirror like this will give you an enlarged image. A flat mirror will give you an image the same size as the object. So that's a virtual image. If you put a 3x5 card back here behind the mirror, well, there isn't really any light falling on that card. It just seems, the light seems to come from there. But since there's no light falling on the card, no image will be projected on it. Real images can be projected on a screen. Virtual images cannot. Ray diagrams for a lens are kind of similar. I've got an example on the formula sheet that I'll refer you to instead of belaboring the point. So, some examples to see how much of this you've absorbed. Now, the equations we're going to be using, well, not only the equations, but the techniques for the ray diagrams also, they assume that it's a thin lens. Similar things will happen with a thicker lens, like a crystal ball, or, you know, what happened to us once a number of years ago, we'd gone camping and I'd saved some glass bottles to carry water in, you know, because I don't entirely trust plastic. I might as well give up because all the plumbing is plastic these days. But anyhow, we had these glass bottles full of water, And there was it was a nice sunny day, and one of them was sitting next to a tarp we had thrown on the ground there. Came and looked at it, and there was this burn mark going across the tarp. It had made a hole right through it with brown edges around it. And that bottle of water acted like a lens. That tarp just happened to be the right distance away, that it was pretty much at the focal point. And the image of the sun just, because you concentrate so much sunlight down into a small area, it gets really intense. And we were kind of lucky we didn't start a fire or something like that. Who would have thought you can start a fire with a bottle of water? That seems kind of contradictory, but anyway, that would be a thick lens, or a crystal ball would be a thick lens. And they behave in kind of similar ways, but you get into the exact details of the formulas, and they assume a thin lens for them to work precisely. So because we're talking about a thin lens, which is supposed to be, the surfaces of it are just a small piece of a sphere, you don't have to go to the trouble of getting out a compass and striking an arc like I did on the pictures further up the page. If you just take your ruler and draw a little line to represent the lens or the mirror, that'll be just fine. So that's what I've done here. So in each case, you're supposed to apply what I said further up the page here, in parallel to the axis, out through the focal point, and so on. And we'll pause here for a moment. Okay, so some sketches here to kind of get the idea across. And once you've been drilled on that, we won't get to it today, but what this will ultimately build up to is a problem you actually get out a ruler and solve properly. But first of all, this is a lens. One of the people, well, it happens sometimes people don't read the fine print and do the diagrams as if it was a mirror. The light goes through a lens, okay? And then number 4 on the next page will be a mirror. But results should have looked like this. The live students have left a minute ago, so I can unmask. So there's the axis, there's the lens. Focal points are equal distances to each side. And in parts A, B, and C, the object is outside the focal point. And then in the second half of the question, it'll be inside the focal point. So a candle, or whatever it is, in a slide projector, this would be the slide, except nobody has slides anymore. It's all done electronically. So this would be an array of little LEDs, I guess, or no, not LEDs, LCDs, liquid crystals. In a modern projector like that one that's hanging up there near the ceiling. Anyway, a light ray that approaches parallel to the axis passes through the focal point on the way out. Part B. There's the axis, there's the lens, focal points, equal distances to either side. The object's over here somewhere. If a light ray, I didn't really kind of get into a lot about lenses when I was talking about this a little earlier, but a light ray that hits the center of a lens just goes straight through, because it's like window glass there. You got a piece of glass that's shaped like that if you look at it from the side. And if a ray hits it right in the middle where the sides are parallel to each other, then the ray enters the glass, it refracts, But then when it gets to the other side of the glass, it refracts back to its original direction. And if the lens isn't very thick, it basically just went right straight through. The little jog that it makes inside of there doesn't amount to anything. So you just take your ruler and you just draw a straight line like that. And that's what happens when the light hits the center of a lens. Little different than a mirror where we were talking about the center of curvature, which is not a point on the mirror. It's a point off, to the side of it. Part C. Focal point there, object over here. Array that, well, it's the same idea as part A, except in and out are switched. Here it was approaching the lens parallel to the axis, and then through the focal point on the way out. Now it's going to be approaching through the focal point and parallel to the axis afterwards. So in parallel, out through the focal point, in through the focal point, out parallel. Same idea, just turned the other way around. So like that as it approaches the lens, and then after it's refracted, it does that. And then we do the same things again, except it'll be an object inside the focal point, like what you'd have if you had a virtual image instead of a real one. So focal point there and there, maybe put the object here in parallel to the axis, out through the focal point. Same thing as part A. The ray that hits the center of the lens still goes straight. Same as in part B. A little steeper this time because the object's closer. Point there, focal point there, object somewhere around here. Incidentally, when you draw these diagrams, the tail of the object belongs on the axis. Okay, you draw two or more of these rays and you look for where the rays cross. If the rays came from the tip of the arrow, that'll show you where the tip of the arrow is on the image. If the tail is on the axis, then the tail of the image will be on the axis. If you had it somewhere else, you'd have to draw another set of rays to locate the other end of the object or the other end of the image. So tail goes right on the axis, like I've done all of these. So part F, I should have made my lens a little taller. This is a ray that approaches the lens from the direction of the focal point. I'm drawing this part dotted because there isn't really any light traveling along that part of the line. Light starts to follow it here. In from the direction of the focal point, out parallel to the axis. Really the same general idea as part C back here. Comes to the lens from the direction of the focal point, out parallel to the axis. Okay, well, you may or may not have noticed that if you turn the page over, there's more of the same types of examples for you to work on. In case you don't have the handout sitting there next to your computer, I'll get it on the camera where you can see it. So same questions, except now it's a mirror instead of a lens. So the light ray bounces off instead of going through. So if you haven't already, pause the recording, work on these. And in fact, there's a number 6 that doesn't quite show on the camera yet. So work your way through those. And after you've given it a good try, play back me going over it. Hard A. There's the axis, there's the mirror. And again, it's actually supposed to be not a flat mirror, but a curved one, but it's such a small part of a sphere that if you want to just take a ruler and, you know, it'll be close enough. Kind of like the Earth looks flat if you have a small enough piece of it. Center of curvature is here. The focal point is halfway from there to the mirror, and looks like the object is out here somewhere. So, just like I was saying with the lens, if it approaches parallel to the axis, it goes through the focal point on the way out. It's just this time it bounces back the way it came instead of going through. Part B. Center of curvature there, focal point there. Object over here somewhere. Maybe I shouldn't have made it so big, but it'll be all right. So this one was in parallel to the axis out through the focal point. This ray goes in through the focal point and out parallel to the axis. Part C. Might want my mirror a little bigger for this one. You know what, it'll fit better if I've got the object a little farther back. Anyhow, after all the fussing around, the point is that a ray that approaches through the center of curvature hits the curved mirror perpendicular to its surface and gets bounced back the way it came. And then part D, D, E, and F are the same thing again, but with the object inside the focal point, like you'd have with a virtual image. There's the mirror. Center of curvature is about there. Focal point's about there. Looks like I put the object over here. In parallel to the axis. The ray goes out through the focal point, just like in part A. A ray that approaches the mirror from the direction of the focal point. In other words, it's moving along a line that goes through the focal point. From here to here, I made it a dotted line because there isn't actually any light moving along there. It's just an extension. You know, geometric lines go to infinity in both directions, but there's only light moving along that line from here to here. So light that approaches on a line that goes through the focal point is parallel to the axis afterward. Same basic idea as B. In through the focal point, out parallel to the axis. In on a line through the focal point, out parallel to the axis. And the last part is the one through the center of curvature. Well, same sort of thing. A geometric line goes to infinity in both directions, but light only starts traveling along that line here at the object. But if you were solving a problem with a ray diagram, what you would do is you'd get your ruler lined up with the tip of the object and with the center of curvature. I don't know if it really matters if you draw the dotted line or not, but light actually begins to move along that line here. And then the mirror bounces it back the way it came. So maybe I shouldn't have been so fussy about that being a dotted line, because I'm just going to draw over the top of it. And that's the way the light heads back out again. Number 5. What does that say? I should boost that up a little so you can see number 6. You still can't see number 6 because it's all fuzzy. And I have no idea how that hand thing works, but it works. Something to do with the autofocus. Sketch at least 2 rays from the tip of the arrow, as in problem 3, to beyond where they cross. Okay, this time, instead of just drawing rays, I want you to, on a kind of a crude sketch at least, I want you to locate the image. And it's the same thing. Same thing in number 6. In one case, you've got a lens, the other case, you've got a mirror. And so if you haven't already, pause and do those. Locate the camera. Number 5. Make a quick sketch of what's given with the question. We've got the axis of the lens going along there like that. The lens is somewhere around here. Focal point. Equal distances to each side. Fairly close, I guess. And the object is somewhere around here. So draw at least 2 rays and locate the image. It doesn't matter which 2 of the 3 rays you draw. Any 2 of them will show you where they cross. If you have a little extra time and inclination, you can draw all 3, but I'm going to take the lazy way out and just do 2 of them. So maybe I should label my focal points for what they are. A light ray that approaches the lens, well, that's supposed to be parallel to the axis. Yeah, sort of. That's going to go through the focal point on the way out. And then for the other one, I chose the ray that comes from the other focal point. And that's going to be parallel to the axis on the way out. So the way you solve a problem with a ray diagram is first you draw the background, the axis and the focal points and the lens and the object. Next, you draw at least two of the rays. Use a ruler so they don't come out looking like that, which isn't anything like a straight line. And then to locate the image, you look for where the rays cross. Well, these rays never do really cross. They're diverging from each other as they move away from the lens. So because they don't really cross, you don't get a real image. But if you're over here looking through this thing, okay, you're using the lens as a magnifying glass. Maybe this object you're looking at is some fine print that you're trying to read. And so your eye is over here, you're looking through the magnifying glass. This ray enters your eye as if it had come from this direction. This ray enters your eye as if it had come from this direction. They cross here. So that's where they seem to have come from. So you've got a virtual image back there behind the lens. When you use a magnifying glass, that's a virtual image because, well, for one thing, I'll probably repeat this as we go along a little further through this, but when it's a single lens or a single mirror, virtual images are always right side up. Real images are always upside down. When you've got combinations, like in a telescope or a microscope, two or more lenses and or mirrors, anything can happen. You can have virtual and inverted or, whatever. But when it's just one lens or just one mirror, a virtual image is always right side up. So a real image is not what you want for a magnifying glass because, well, I suppose you could turn the page so the page was upside down and then it would look right side up through the magnifying glass. Maybe that wouldn't be so bad. Anyway, number 6. Similar question, this time it's a mirror. And this time the object is outside the focal point, so we'll get a real image rather than a virtual one. The object is there. Center of curvature is about here. Focal point is halfway between there and the mirror. So again, sketch at least 2 rays and then locate the image. Doesn't matter which of the 2, or sketch all 3 if you want, but doesn't matter which 2 if you do only 2. I did the one that's in parallel to the axis and out through the focal point. And for the other one, I did the ray that goes in through the center of curvature. Made my mirror just barely big enough, apparently. That one reflects back the way it came. The reflected rays, not only the 2 I've drawn, but all the others for that matter, will cross here. So since the tail of the object is on the axis, the tail of the image is on the axis. The tip of the arrow is where these rays came from. The tip of the arrow on the image is where they cross again. So you can see that the top comes out below the bottom. That's what I was saying a minute ago. A real image is inverted. A virtual image is right side up, if it's just a single lens or a single mirror. Okay. Well, the next thing for you to do is the third recording is going to be a pretty short one. I suppose I should point it at this. What I want you to do now is just basically the same thing as the two previous examples, only actually get out a ruler and draw it to scale and try and get a, try and measure a correct answer off of the thing rather than just a sketch. Yeah, that's the whole thing. So what the rest of this page is just trying to talk you through step by step how to do it. Step one, draw the axis. Step two, draw the mirror, draw the focal point, center of curvature, and so forth. I guess that's still part of step two. Draw the object over there. So the first two steps, that's just creating this picture drawn accurately to scale. You want to pick some scale that on the one hand doesn't make the picture go off the edge of the page. On the other hand, you want to pick a scale that, you don't want to end up with some little microscopic drawing either, where if you're off by a millimeter, it throws you off by 25% or something like that. You want to pick something convenient. You don't want a scale that's like 17.4:1 or something weird like that. Nice round numbers. But aside from that, something that comes fairly close to filling the page without going off is what you want to pick for a scale. So you draw the background, the mirror, well, you should make it look just like this. Or if it's a lens, just like that. And then you draw the rays, like in the example that we just spent a lot of time on. And so on, as is continued on the next page. Maybe I don't need to put that on the camera. You draw the rays, you look for where they cross, and then measure things like how far that is from the image, or how far that is from the lens or mirror, and how tall it is, and so forth. So what you need to do now, well, either now or when you sit down to play back the 3 out of 3, the third recording in this section, is you need to do problem number 7 on the next page.